jump back into ANOVA stuff. Okay, cool. So we went through last time, I just gave you this handout. We'd gone through and worked our way through our screening. One thing I just wanted to do here is just spend just a little bit of time before we move on, recapping. Okay. Flip to the back page, or the back couple of pages here. Just want to have you take a look at the write-up. Again, I don't like providing a lot of templates, because my concern is that people just use templates and sort of cut and paste and plug things in and not have a good understanding of what's actually going on. But for the purposes of these screenings that we'll be doing increasingly moving forward, don't be a hero, don't invent your own thing. Just go through and use this. This is actually a nice way to just kind of go through and structure. It seems like sort of several pages, but it's actually not too bad as you're going through, working through your screening, just kind of plugging stuff in, making sure that you're got everything put together. So here, remember that we didn't have any missing data. We didn't have any problems with problematic values. For these data as we move forward, don't screw around or fool with data or try and smooth or transform or anything unless I tell you to, because that's too much to try and figure out what CJ's done to transform things versus what tomorrow's gone through to transform things. If we have values that are clearly implausible or values that are missing, we'll just get rid of those cases so that we're all running the same data. But if you want to just go through, or you would just say, tell me how many people are in the sample that you're actually screening, that's helpful so I know. Here we're looking at a group-based analysis, right? So we have to go through and look at distributions individually within each group. Right? Each one of these groups is its own population that we're going down through and working. So we've got our participants who identified white non-Hispanic, talking about skew kurtosis distributions for valence and arousal there, giving a brief description of the histogram and box plot. Same thing for our participants who identified as black non-Hispanic, and then our homogeneous group of others, which is problematic for the actual real interpretation, but so it serves a purpose for this example. Same thing, outliers and extreme values, wanting to go through and making sure that that we're calculating Z values. Want to split that file before we actually go through and start running Z scores. Chris, why do we want to split the file before we start running Z scores? Right? Because otherwise what we're doing, we're calculating Z scores based on the total mean as opposed to group level mean standard deviations. That was the error I found when I had gone through. I had ran Z scores before I flipped it, and you won't notice that because it won't tell you. So you just want to go through what is one way that you can go through and determine whether or not you've calculated Z scores correctly for each group. If you've done it correctly, what should the mean and standard deviation be for each individual group?
Mean should be 0, standard deviation should be 1.
Right. And if you go back through and take a look at that other handout, if you go through, and I broken it down by group, but if you looked at the means and standard deviations, they weren't 0 and 1 for each group, suggests that there was something wrong, right? So you want to make sure that you go through and do that. Go through, talk about Levine's test. For these data, we did not have much evidence for a violation of homogeneity variance with respect to valence, but we did for arousal, okay? And so then once we go through and do this, this last piece is where I want you to kind of tie it all together and just give me a quick kind of summary of what this means. Your role here should be, think about yourself as statistical consultant, right? I've done this type of stuff before, and it's rewarding and not rewarding in certain types of ways because people will bring you data and they'll say, here's what this is what I have, this is what I want to do. And you have to go through and say, well, you can't actually do that, or you shouldn't do that. This is the problem with that, but these are the things that we need to be careful of. Like, this is where you kind of pull this together and give your recommendations. So here, I've noted that we have an unbalanced design with a modest sample size for our other group. We've got low rating of valence in our white non-Hispanic group, And then we have likely violation of homogeneity variance for ratings of emotional arousal, right? So just kind of identifying what the main issues are, and then down here kind of tying it together, talking about racial ethnic groups in the sample are imbalanced, with a limited number of participants in the other category. Analyses also suggest possible violation of homogeneity of variance for ratings of emotional arousal groups, with the highest being our black non-Hispanic group, and our lowest, our white non-Hispanic group. Variability in self-reported arousal similar in size, possibly helping mitigate bias in the ANOVA test of differences. Okay. Any ideas on why I'm saying, why I'm concluding that the sample sizes might help mitigate potential bias in this ANOVA test? This is kind of an extension of some of the things that we had talked about with our independent sample t-test.
Probably using sample size increase the representation of the
Okay.
population members.
Okay, so my bigger samples, so my white non-Hispanic, my black non-Hispanic, probably are a more precise estimate of variability. What else? What happens? Let's say I have a paired sample test. I just have two groups, right? And I have violation of homogeneity of variance, and my group with far more people has a much larger variance than my group with my smaller people. What am I concerned will happen if I don't do any sort of correction for homogeneity of variance? My group with more people has a considerably higher variance than my smaller group. What is it?
Weighted, the variance can be weighted towards that group that has more.
Right. Right, and so in my test statistic, we're using the pooled variance, right? So I only have one variance estimate. Am I concerned that variance estimate is going to be inappropriate, too large or too small?
Sorry, say that again.
Am I concerned that my pooled variance then is going to be too large or too small?
No, too large.
Too large. And if my variance is too large, what does that do to my test statistic?
Deflates.
It deflates it, it makes it smaller, and my standard error is too big, right? I'm assuming that the variability in these two groups is equal, and it's not, but I have 4 times as many people in this group than that group, and so my larger group is going to get weighted more, and so what it's going to end up being, my pool variance may not be actually a very good representative or very representative of my smaller group, right? If I switch it around, my really big group has a really tiny variance, right? Then what's my concern? Yeah, my pool variance is going to be too small. It's going to jack up my test statistic, and so my test is going to be too liberal, right? So in this case, we have 3 groups, right? And we have, in terms of arousal, we have evidence that we possibly have violations of homogeneity of variance. But my 2 groups that have similar numbers of people, one group has the smallest variance, largest group, the other group has the largest variance. So it kind of cancels each other out, maybe, right? So this is one of these things. It's easy to go through and say, oh, well, this is wrong, and this is wrong, this isn't perfect, and so there's also this thing, right? It's another thing to sort of know enough about this to go through and say, what are the actual consequences for my data, right? And this is super important. If you've got a situation where you know that just the nature of my test may systematically inflate my standard error, and then I get a test statistic that's kind of right on the border of what I can claim as, or what I can publish as a significant effect, right? I might want to say, and I've done this before, saying, well, so these data are marginal, however, characteristics of the data suggest possible inflation of the standard error in this, therefore, sort of taking this into account in terms of making my, so strengthening my argument for, hey, we should look at this thing, because basically the violation has caused something that will likely inflate this statistic, right? And then we publish it, right? So apparently I made a convincing argument, but this is where sort of knowing exactly what's going on is going to be helpful. So I don't expect you, as sort of new into this, to be, I don't know all the ins and outs, but at least be thinking about, okay, here's a violation or here's an issue that I have detected in my data. What are the likely consequences? Okay. So. Also saying, so one student identified as white non-Hispanic, case number 68, reported an inordinately low score for valence. So sort of writing in sort of what that was. However, individual expected to have minimal impact on group mean given the sample size and the range of the scale. So basically, we're saying we've got someone who is a low score. They're over 3 standard deviations below the mean, right? But it's one person, given the size of the sample, they can't be that far out, right? It's not going to be like, and we talked about this before, it's not like if I'm measuring income and someone can be an outlier, super outlier, right? And so it's likely to have, I'm saying, at least in my professional opinion, it's there, but we don't need to worry about this. I'm going to say also recommend the use of robust tests for evaluation of group differences in arousal. And then right here, remember this is a recommendation from Howell, considering possible explanations for observed differences in variability. Probably the most important thing we get out of our screening is a really good and intense familiarity with our data, right? So I feel when I'm in some sort of thesis or dissertation defense, I shouldn't be able to, like, if I ask you a question about your data, you should laugh at me because you know exceedingly more about that data and spend intensely more time with that data than I have, right? Sort of going through allows you to sort of understand, one, do I have problems with any potential statistical tests, and two, what's going on, right? I've seen that this group has, I'm seeing large variability across these different groups in terms of variability of emotional arousal, okay? Now, the whole idea behind this example is that we're going to look for mean differences in across a diverse group of students, looking for differences in emotional ratings of emotional response to a film that contains white non-Hispanic actors, right? So I want to say, so are we getting the same, is this film doing the same thing across different groups, right? And so if we don't, let's say we do notice that there's different variability, that we have what looks like sort of observable variability or differences in the variability of scores, but we don't see any difference in scores, is that still meaningful? So I'm not seeing mean differences across my different groups, but I'm seeing considerable differences in terms of overall variability. Is that something that's interesting or not interesting? Yeah. So in our means-based analyses, we talked about this last time. If this is the distribution of my group and this is the mean, what do I call any score that's not falling exactly on that mean? What's up? Different.
I mean, deviant, it's
Yeah.
standard deviation, that's the difference.
Yeah. Which means because everybody in this group has all gotten the same thing, right? If whatever I've done to this group, what should everybody's score be? The same. And if it's not, what are we calling it? Error. Error. That's right. Right. And so if I see more variability, right? See, we can get these guys separated, right? So some crosstalk. You're chirping. Error. Right.
Well, my ears certainly feel better tomorrow.
So if in this group I'm seeing, so if among my white non-Hispanic group, if I'm seeing less variability in scores relative to my other score, it's suggesting I'm getting more error around that mean value in the one group than the other, right? And so even though my mean values might be the same, it's suggesting that there is something maybe going on different in this other score, because people are much more variable, right? This film is providing less consistent ratings in sort of this group as opposed to that group. And if it's gotten to the point that it's been detected as sort of reliably different in terms of the variability, it suggests that, okay, on average, this film might be working the same. But when I start to look at specific minority groups, I start to get a lot more variability. People are either just really high or really low. Not everybody's lining up in the exact same spot. And if we go through and we take a look at the box plots for arousal in this handout, tomorrow, what are you seeing here?
There's a lot more variability in black non-Hispanic individuals.
Right. If I'm looking at this, the means might not be different. But there's it looks like there's something that's not the same going on in this, right? And sort of consistent with our hypotheses, right? Social psych research suggesting that we tend to be sort of read things better and are more responsive to people who are more like us as opposed to different than us. And so wanting to think about within the context of it now, I'm not doing an official test, so my hypotheses aren't about variability across groups, but this might be something that I might want to talk about in terms of discussion, say, well, we didn't actually find differences across these groups, but we did find evidence of greater variability in this group as opposed to this group suggesting that on average people might be responding about the same, but within groups much more variability around sort of people's responses than in this, right? And this starts to become relevant for our experimental designs, because if I'm giving someone a manipulation, TJ, you're giving someone a manipulation to try and sort of impact change on things, you want everybody to be responding to that manipulation in about the same way. If people are all over the place, it works for some people, it doesn't work for some other people. I start to worry about the strength of that manipulation, the efficacy of that manipulation, right? So again, not wanting to just say, oh, hey, we found weird stuff, and so we're just gonna ignore it, right? We might want to go through and think about that a little bit more. Another example, anytime I'm seeing, if we look at on the other group, the histogram for valence, right? This is looking like, Alicia, how would you describe this this histogram for valence here for our other group? Yeah, it looks kind of bimodal to me, right? If this is my study, and I think about what I've done with this group is just basically takes anybody who's not white or black, non-Hispanic, and sort of grouped them together. I might start to worry I might have different groups going on in here, right? So this is my data. I might say suggest maybe this is, so I had a small collection of people who identified primarily as Hispanic, and a small group of individuals who identified primarily as Asian American, an Asian who might be popped in there, and so maybe I'm saying, oh, maybe grouping people into a non-specific other category wasn't the best strategy to go, right? Or it could be for this specific group, I might find, I might be seeing gender differences, right? Given the nature of the clip, women might find it funny, men maybe not so funny, right? This is the diner scene from When Harry Met Sally, right? You can see maybe differences in how funny people think that is, right? Sort of given the context and the stuff, right? So again, these are things that in our screening, we want to go through and have a very, very detailed understanding of what's going on with these data and starting to point out. We don't want to over-identify things, right? That's probably for people who are new into this, start to over-identify things and say, well, this person is 3 standard deviations above me, therefore these cases are outliers, and so we're going to eliminate them. That's not, don't do that, right? But just wanting to think carefully about what are the scores that we've observed, how do those map on to what we've done, and what does this tell us about possible phenomena that we're interested in, okay? Cool, all right, so we spent a bunch of time doing that. Now, we did to jump right in, just run our ANOVA, right? Which, once we've spent 2 hours going through screenings, this is sort of anticlimactic, right? So we go down to compare means, down to one-way ANOVA. We'll put emotional valence, emotional arousal as our outcomes. Ethnicity is our factor. We're going to go to options. We're going to request descriptive statistics. We're going to ask for homogeneity variance tests. And we're going to ask for a Welch's test. Okay? This is our corrected test for violations of homogeneity variance and unequal sample sizes, which we have both here. So we want to go through and select this. Doesn't mean the plot is kind of terrible, but we request it anyway. Okay, and then here, go through and paste. But go through and run it, and is what we end up with. Okay, so up here we have our descriptives. We just spent a whole lot of time working through screening, so we don't need to spend too much time being concerned about this. But do go through and take a look at it and make sure that you have the right number of people and that everything looks like things should, right? One thing that I like to do is mislabel my category or my categorical data. And so if I see that I have the majority of my people are other, that suggests that maybe I labeled that wrong. Want to go back to and check that. So we have descriptors for valence, arousal, mean, standard deviations, 95% confidence intervals around mean values, min, max. Shouldn't be anything shocking come up in this after we've just gone through and run our screening. Okay. But down here is where we get our homogeneity of variance tests, right? We didn't do this in the screening, but this is where we get it in. So we go back at it in. We see here what we're going to be doing. SPSS has expanded out this a little bit. There's more options than it used to be. We're just going to focus on based on the mean here. And we see what is our conclusion? We said, do we have concerns about violation of homogeneity of variance for emotional valence? No, looking pretty good, right? But what about for emotional arousal? Yeah, looks like sort of there's at least something there that suggests that I might have differences across my groups. And if I see that, I'm probably going to maybe take a quick peek up here. Now these are standard deviations, not variances. As soon as I square my standard deviations, what's going to happen to the observed difference between those numbers? It's going to get even bigger, right? But right now it looks like my for valence, my black non-Hispanic group had the largest amount of variability. My white non-Hispanic group has the lowest level of variability. My other group kind of falling in between there, right? So it looks like probably my best guess is that there's probably some difference in variability in responding across my participants who identify as black non-Hispanic and white non-Hispanic. So wanted to think about that before we go down and take a look at results of our ANOVA. Drop down to our ANOVA tests. Siley, what are we seeing in terms of our omnibus test for emotional valence? What's that?
So, can you repeat the question?
Yeah. So so I'm going through, taking a look at my ANOVA table. If I'm thinking about emotional valence, what is my what am I seeing here based on my ANOVA table? In terms of just general conclusions.
There is fails to judgment.
Okay, right. So we're doing straight hypotheses testing, right? We would say that these, maybe we could say that these, based on the omnibus test of group differences in valence, we're seeing that these data seem relatively compatible with the null hypothesis of equal scores across groups, right? Our p-value here is fairly large, right? Again, if we're thinking about p as continuous evidence against the null, it looks like these are not unreasonable given our null hypotheses, right? Also want you guys to be looking at what is my sum of squares? What does my between group sum of squares correspond to? Nick?
The combined variance in all those groups. Right. For the
Okay, so
the mean difference.
yeah, my between group, right? This is the variability across my mean values across my groups. This is the sum of squares, the sum of the squared deviation scores from my group mean relative to my grand mean, right? Assuming that we're interested in claiming an effect, Nick, do we want to see relatively larger between group sum of squares or smaller between group sum of squares?
No, larger ones.
large orders, right? Because this is telling us, this is our measure of variability. Remember, in ANOVA, variability variance just means differences, right? This is our between group differences, okay? What about our within group differences? Chrissy, what's our within group sum of squares telling us?
The variability within each group.
Right, right. And so we've got variability within each group, right? And what do we call variability within each group?
Variance.
Well, it is, what type of variance?
Error?
Error, right?
Yes.
Because again, if racial ethnic identity was the only thing that was determining valence, there should be no variability, right? Everybody, because we're all part of the same group, everybody should get, now this is pre-existing individual difference factor, not an experimental manipulation, but anything that's not consistent there is stuff that we haven't accounted for in the model, which is by definition error, right? So this is within group variability, this is our error, and then the total, this is just the total variability in the whole sample. If we actually, yeah, if we were to take our total variability here, so I'm taking 180.182, 180.182 and divided by 98, what am I getting? Yeah. So someone with a calculator. Take my, take your total variability, or your total sum of squares, 180.182, and divide it by 98, which is our degrees of freedom.
1.839.
Okay. So you get 1.839. Okay. Who did that for me? Chris. All right. Take 4 valence. Take this total, the standard deviation for the full sample, 1.356.
Square it.
And then square it.
Take that.
Yeah. 1.839. Okay. This helps. So this is going to be useful when down the road when we start trying to break apart different pieces of components. Our totals, our sum of squares total here is just the total sum of squares for the whole sample, right? If we would, if we take this, divide it by this, we get a variance estimate, right? And so our between groups mean square is just a variance estimate, different function of sum of the squares, mean squares is just variance, it's all a measure of variability. This is just a little bit easier to work with. This is our within group variance. Divide those two, get our F, and the rest of it gets back. Okay. We kind of see how, remembering how this kind of fits together. Okay, cool. So it looks like we don't have compelling evidence for differences in readings of emotional valence across groups. We also didn't see variability. Looks kind of similar in terms of that. We didn't have a violation of homogeneity, so it looks like maybe not too much going on in terms of differences in terms of ratings of general pleasantness in response to this film. Okay, but what about emotional arousal? Do we want to go? Yeah,
But,
Go.
preemptively raise my hand.
yeah. Okay.
I
So-
can do it.
Go for it. Okay. So emotional arousal. So what are we seeing here, and maybe what might we want to think about before we sort of jump to conclusions here?
Before we jump to conclusions, we need to consider what contributes to the p-value itself.
Mm-hmm.
But just based upon the p-value, you could say that there is some evidence against the null at this point.
Okay. Based on this, but do we want to trust this this standard ANOVA model?
No,
Why not?
because it doesn't tell us exactly where those differences are occurring.
Right. Well, in terms of mean values, yeah. But remember, we also had a violation of homogeneity variance, right? Suggesting, so we've got different sample sizes, we've got different variability, suggesting that this is probably not a good or reliable test for what we're wanting to do, right? We've got too many violations. So what we're going to do is we're going to go down through and take a look at our Welch's test, right? Remember, Welch's has a corrected F, a corrected degree of freedom. And what do we see now when we run this robust test for equality of means, accounting for differences in variability and difference in sample size? What is our conclusion now? Yeah.
We're happy with that.
Right, we are, right? Now, again, with everything else that we've talked about, we probably want to be cautious, right? This p-values is providing us evidence that sort of there may be differences across these groups. It's not the most compelling evidence, right? Sort of by our general standards, right? We're well within our right to claim that sort of we've found something worth exploring or sort of taking even further. But again, this is where maybe some supplemental statistics might be useful in going through and taking a look at strength of evidence here. So for this problem, if we go through, we're just focusing on arousal here. My base factor bound is 3.02. My S value is 5, right? So based on this corrected test, I would say that evidence against the, sort of based on my Welch's test here, evidence against the null, or sort of these data provide similar evidence against the null hypotheses of equal ratings of emotional arousal across monoracial ethnic groups. Is similar to receiving 5 consecutive heads of a hypothesized fair coin, right? If I get 5 heads in a row, am I starting to question whether or not Chris C is using a fair heads on this coin? Yeah, I'm starting to get suspicious. Am I confused? Am I ready to like gun you down in the street? Call you a cheating liar? Probably not yet. I'm not that aggressive.
So violent.
What's that?
His deaths are so violent.
So my own sort of sublimated anger, right? It's very intense on, right? So it's evidence, but we want to be cautious about, stuff here, right? My base factor here, saying that based on the data we collected, the odds of the alternate hypotheses of different arousal ratings across racial ethnic groups looks to be at most 3 times the odds of equal scores across within these different populations, right? Something along those lines. Remembering that we're talking about odds here or likelihood, right? So we can talk about this is odds is 3 times that of HO, right? We could talk about a 200% increase in odds, right? Something along those lines. We've got to play around with that. I want to talk about that a little bit. Okay. All right. What's the last thing we might want to do based on this omnibus test here?
Effect size.
Effect sizes, yeah, right? And what are my options, Chris, for effect sizes based on my ANOVA model?
It's there's the weird W,
Yeah.
and then another Greek letter.
Yeah.
So either one of those.
Yeah. We can either calculate weird W or weird N, right? Whichever one we want. Right? Or eta squared, right? Or omega squared. Someone tell me, anybody remember what the difference between eta squared and omega squared is? Tomorrow?
Eta squared is correct.
What's that?
Doesn't it look correct for something?
Which one?
Eta?
8. What do you got? Okay.
Eta is the sample statistic, and omega is the population statistic.
Good, okay. Both eta and omega squared they're measures of association, and both are going to be positively biased, right? Because I can't account for negative variance, right? Even if there's just random static, it's going to give me an eta squared and omega squared that's greater than 0, right? But what we know is that eta squared is a nice descriptive statistic. It's saying in these data, but it's a biased population statistic. Omega squared, still biased, but less so, right? And so the nice thing about eta squared is it's pretty easy to calculate. in that we're just taking our sum of squares for our between group or our variability across group, right? So we got 7.714 over our total variability. Sum of squares total 180.182 gives me an eta squared. Whoops, look at the wrong one. Well, I was calculating for valence, but we won't worry about valence for right now since it doesn't look like there's much going on with that. So, here we go, 16.693 over sum squares total, 289.636. Can give me an eta squared, 0.058. Okay? And again, wanting to think about when you're doing these and trying to get a good conceptualization, think about what's actually going on here, right? If we think about sums of squares as a measure of variability, right? We've got measure of variability that's accounting for differences between our means over all the variability in the sample, right? This is just a basic percentage, right? So what we're saying is group differences account for about 5.8% of the total variability in this sample, okay? And if we're looking at benchmarks for eta squared, have that up.
Yeah.
What is it?
Small is 0.01, medium 0.06, large is 0.14.
Okay, so we're getting close to a medium effect right here, right? So I mean, 6% of the variability may not seem like a whole lot, but it's better than what we often get with this, okay? But we know that this is a biased statistic, right? And so what we might want to do is calculate omega squared. And omega squared is going to be sum of squares my treatment minus k minus 1 and mean square error over sum of squares total plus mean squared error. Okay. So if we go down through, we calculate this, we've got our sum of squares total 16.693 minus, how many groups do we have? 3. 3 minus 1 times my mean squared error, 2.843, all over sum of squares total, 289.636 plus 2.843. Okay. Which gives me a value of 0.038. Alicia, based on what we know about eta squared and omega squared, do these values make sense in comparison to one another? Yeah. Why? Somebody want to help her out?
Because the eta squared is more positively biased versus the omega.
Right. And so we're saying here, we know that eta squared is a positively biased statistic, right? And if we think that omega squared is still biased, but less so, right? It would make sense that our omega squared is slightly smaller than our omega, or than our eta squared, okay? Now, when we're going through and we're calculating confidence intervals around our effect size, we need to use eta squared, right? Because again, this is the variability that's going into calculation of the F, which is going to go through and calculate the upper and lower bounds of your 90% confidence interval for omega squared, remember, or for eta squared. But sort of this is a better population estimate of things. Okay. All right. Questions about sort of this, just the omnibus sort of ANOVA test?
So would you use the omega square when you're talking about effect size, and then the eta squared for the confidence, or the NC, when you're calculating your NCP?
Yeah, this is actually, I mean, it's a good, probably best practice would be to provide both of them, or you could provide, I mean, it's sort of like in regression. And again, I can't, anybody background in regression thought about it as inflated, and some people say, well, you should probably present an adjusted R squared, but depending on sometimes it's a bigger adjustment or not. Probably if we're thinking about providing good estimates, we should be thinking about providing omega squared, right? As soon as I finally sort of deciphered how to go through and actually calculate confidence intervals around this, I got excited about it until I actually did it, and then it's probably, I don't know, I would start to question, because again, can we have values of eta squared or omega squared that are less than 0? No. And if a medium effect is 6% of the variability, given the size of our samples, when you actually go through and start calculating confidence intervals around these omnibus effect sizes, what's the lower bound? A lot. 0, right? And so we've got effect sizes that consistently grab 0 as the bottom and sort of up. And so it starts to become, I get less excited about confidence intervals around these measures of association than I do around like point estimates of our pairwise effects. People have made arguments that calculating confidence intervals around effect sizes isn't useful because the intervals are so large. I would disagree with that. I think that starts to make us uncomfortably aware of the imprecision in our statistics. But in this case, probably what I would do, and what I'll encourage you all to do, unless otherwise specified as we move forward with stuff, just report an interval omega squared, right? If people go through calculate eta squared on their own, it's pretty easy and straightforward if you're providing sort of relevant statistics there. Does that help?
Yeah, so you would use like the eta squared if you wanted to figure out your abscess.
If you wanted to, if you were hard up, if you had reason to calculate a confidence interval around this omnibus effect, but we often don't, which we'll talk about here in a moment. But if I did want to calculate a confidence interval around a point of estimate of this omnibus effect, then I would use eta squared for that. But otherwise, if we're just reporting a point estimate, a population estimate, probably omega squared is the better statistic to report here. It's kind of a bummer because it's always going to be lower than your eta squared, but at the end of the day, no. We really don't care about omnibus tests all that much for reasons we'll talk about in just a moment. Questions? Okay, cool. And then down here, you just, this is better. So the upgraded SPSS is doing a little bit better. So this is just giving you graphs of your means. If you want to just take a look at those, and that can be something that's useful. Okay. But we'll jump back into I really like you guys mixed up. It makes me a lot more comfortable. Pressure on me if I feel like I'm giving the guys too much attention and the girls too much attention. Some integration is nice. Changing things up. All right. Just quickly going through screens that you've already seen. Obviously, this is how we're going down through conducting our ANOVA models. This is our output. We just walked through all of this stuff. So, Alicia, for you and using SATA, same type of thing. If you go through and take a look at those two handouts, you'll see the numbers are exactly the same. Just want to know where to go through and find stuff. To get in SATA, you want to request your homogeneity variance test specifically. There's a row bar like you did before, right? Here's your Levine's test for both of these. That's easy peasy. Here's our one-way ANOVA in STATA. ANOVA valence ethnicity gives you everything. Quick, easy. That's what we've got going on here. Our Welch test, if you find a violation of homogeneity variance, you want a Welch test, you just say W test, arousal, ethnicity. Boom, gives you that, right? Here's your Welch test. Margins plot is just giving you sort of different sort of your means-based plots along with confidence intervals, which is nice. If you want to calculate these as bar graphs, there's a thing you can just go through and do that if you prefer looking at bars. But then this is nice, which will be fun for you after you go through and you run your ANOVA. If you just hit E-stat E-size, it's going to give you your eta squared for what are we looking at here? This must be okay. Yeah, it must be. This was for arousal. So this is this will calculate your eta squared for that model in addition to your 95% confidence interval. You can also hit E-stat E-size omega. It's going to give you your omega squared value. So this is nice. Stata will go through and just calculate this for you, so you don't have to worry about sort of cranking that stuff out by hand. So, all right. So, how do we go through and write this up, right? So here, talking about one-way ANOVA models used to examine differences in ratings of emotional valence and emotional arousal in diverse students exposed to them using film clip containing white non-Hispanic actors. So this is thought. You can include this in your write-ups if you want to. You don't have to. This is just kind of a nice orientation, sort of grounding, and sort of talking about what's happening here. Here we say evaluation of responses for emotional valence suggests data relatively compatible with the null hypotheses of similar scores across students from different racial ethnic backgrounds, right? I got my F, my P, my omega, S, base factor, but there's not really much to talk about here. It's kind of, it is what it is, and if that's the case, don't spend a lot of, tell me that you didn't find much evidence of differences, and then we can move on to bigger, better things, okay? What's test for ratings of emotional arousal, by contrast, demonstrates some evidence of possible differences across white, Hispanic, black, non-Hispanic, and heterogeneous other groups. We get a test statistic p-value, omega, BFE. Estimates of omega squared suggest approximately 3.8% of population variability. Ratings of arousal accounted for by racial ethnic differences across viewers. Notice here that I'm identifying omega squared as a population statistic, right? Which is going to be different than the eta squared, so just sort of make sure that you key in on that. Following correction for unequal variances, calculation of base factor bound indicates the odds of different responding across racial ethnic groups are at most about 200 times more likely than the odds of equal ratings of arousal across populations. Whereas data loaded by modest samples, inclusion of that should be not homogeneous, heterogeneous other student group results offer preliminary support for differences across racial ethnic groups in some domains of affective response to standardized film stimuli, right? So this is just me trying to, for this omnibus test, trying to pull it all together, okay? Questions about anything that I've put in there or how I've talked about this, you don't have to go through and in this talk about base factor if you don't want to. I just did to try and give sort of a sense of evidence against the no, right? But kind of up to you on how you want to. I want to give you some flexibility in terms of how you structure what you pull in. If you think it's meaningful, cool. If you don't, whatever. Questions on this? All right. Okay. Let's take a break. We'll come back and we'll get into follow-up tests. How many of you are going to ABCT with ANOVA omnibus test, sort of breaking down, sort of partitioning variability and kind of what's going on with these, with the omnibus sort of model? Okay. So, our omnibus F, as we went through and sort of get that quick interpretation, our test is just, all our test is giving us, all this omnibus test is giving us is just telling us that we have evidence that the mean of at least one population from which these samples were drawn is different than the rest. So again, the idea is that we've gone through and we've got 3 different populations from which we've drawn 3 different samples, right? And our omnibus test is simply telling us that based on the data that we've collected, that it looks like there are differences that there may be differences in the means of at least one of these populations from which we've drawn samples, okay? But that's all the omnibus tells us. Just saying there's something in there somewhere, but it doesn't tell us where that difference actually is. If we want to start to determine which one of these samples are different than the other ones, then we have to proceed with some sort of follow-up tests, okay? Our classic approach to ANOVA models suggests that we need to have an overall, our F statistic has to meet criteria, conventional benchmarks for statistical significance before we start moving on to follow-up tests, okay? When we fail to reject the null or when our alternative test not supported, the idea from a classical approach is that it would be questionable to start mucking around and looking at pairwise differences across these groups if our overall omnibus test wasn't significant. Yeah?
What if it's like 0.055?
Okay. Well, what do you think if it's 0.055?
That we should,
That what?
like we should look.
That you should look, okay? And it kind of depends, right? And this is where we get into some arguments by Howell and others. And in certain areas of psychology, sort of very, very sort of adamant about this. Because again, the classical approach, the classic approach to behavioral sciences is if I don't get a statistically significant, if that omnibus test doesn't tip over into statistical significance, then it's done, right? I failed to provide evidence of differences, or I failed to support or at least find evidence against the null hypotheses of equal means based on the data that I've collected, and so therefore it would be irresponsible and blow my likelihood of a type 1 error through the roof if I start going through and start to tease things apart, okay? But Howell and other methodologists make an argument against this and against the utility of this omnibus test in the first place, right? The argument is that our F tests can start to get diluted when one mean is different from the rest that are all equal to one another, right? So if I've got mean 1, mean 2, mean 3, mean 4, and then mean 5, it's likely that I could get an F test that's sort of marginal and fails to hit that 0.05 test because everybody's kind of mostly collecting right here, and then I've got someone who sort of is, they're just, and it's not a huge difference, but there's something going on there, right? And so problems with the F determined based on the specific patterns of means that we're finding. Other arguments against putting too much emphasis on this F test is that if I start to include my omnibus test, that initial F, and start to calculate that in terms of the number of comparisons that I'm running, problem of making my test too conservative. Basically, I'm having to hit too far of a mark in order to claim statistical significance. And if I have too conservative of a test, what type of error do I run the risk of making? Type 2, right? I'm missing things that are maybe potentially interesting or meaningful. And this is the one I think is probably the most compelling. Omnibus function of tradition and rarely of practical interest, right? And this is why, to start in actual practice, I started trying to do it. Confidence intervals around non-omnibus effect are rarely of interest, right? No one cares about your omnibus test outside of just convention, this being a gatekeeper for then going through and looking at your specific tests of interest, right? If Nick's running an ANOVA model, his hypothesis probably isn't at least something's different than something else, right? And as soon as you find that, you're like, sweet, I'm done. Next thing, right? You have specific hypotheses. The reason you put the whole study together is you probably expect certain groups to be different than other groups in certain directions, right? And the argument is that that's what we're interested in. Why the hell are we worried about the omnibus test? Just go down through and take a look at the test the reason that you've gone through and done this, right? And so from this perspective, this is big in like psychophysiology research and things like that. So more technical areas where like I am not going to put together a study unless I have very specific a priori hypotheses about how this is going to turn out, right? And so then I care less about the F. sometimes I might not even do it. I might just go through and just test the specific hypotheses that are based on the whole reason I did the research in the first place, right? And so, if we're thinking about benefits of our ANOVA model, right, we think about like, oh, well, it helps us reduce the number of pairwise tests and it's more efficient. It's actually not more efficient, because if I do then find my omnibus test, I have to go through and do those pairwise tests anyway, right? We talk about avoiding type of complications with type 1 error, right? If my omnibus test allows me to compare subgroups with one another all at once, but if I do find a significant effect, then I have to go through and run those tests anyway, right? The omnibus test is actually an additional test that I had to run instead of just running the other tests that I wouldn't run anyway, right? And so what we can say is our ANOVA models give us greater flexibility in designing our experiments and sort of in the interpretation of our results, but really good arguments for why we might not put too much emphasis on the results of this omnibus test, okay? Now, this may or may not be compelling to people who are reviewing your research, right? You would want to have, if you decided not to put emphasis on your omnibus test, you would want to make that clear up front and explain why you weren't doing that. This shouldn't be an after-the-fact decision, right? I got it at 0.055 and I'm like, oh, well, this is important anyway, I'm sort of not going to worry about it, right? That's not going to be compelling. But if you can set up and say, for these data, right, I'm very interested in sort of these specific contrasts, whether or not there are differences across, really beside the point. This is what I'm going to go through and do. There's a fairly strong theoretical or methodological argument for foregoing the F-test and just going into specific contrasts of interest. But recognize that you'll be fighting upstream, because most people want to say, well, you've got a group-based design, you need to run this, you need to have a significant effect here before you can move on and test this. But that's actually not considered. Actually, strong methodologists would probably argue that that test is kind of a waste, because we don't really care about it anyway. Okay. Questions on this? Okay, so what we need to do here is we need to start then thinking about managing our type 1 error. When we think about our alpha level, right? This is our per comparison error rate. What we're doing when we say alpha to 0.05, we're saying for any individual test, I'm willing to make a type 1 error at least 5% of the time, right? 1 time out of 10, 5 times out of 10, not 5 times out of 10, forget 10. 5 times out of 100, right? I'm going to go through and I'm going to make a claim that there's something there when there's actually not something there, right? This is my per comparison error rate. But we can then also look at our error rate per experiment. This is the expected number of type 1 errors in a total set of comparison. We calculate this as the number of comparisons times our alpha level, okay? If we go through and then take a look at our family-wise error, if this is the number, family-wise error is the probability of committing at least type 1 error in a series of comparisons. Family-wise error is going to be calculated as 1 minus alpha times to the C power, C being the number of comparisons that we're making, right? So for example, across 4 comparisons, each one conducted at alpha equal 0.05, our family-wise error rate for that set of comparisons is 0.185. Okay? So the argument being that assuming that the null hypothesis is actually true across all 4 of those comparisons, right? So assuming that there is no difference, the likelihood of me saying that there is a difference, even when there isn't a difference, is now not 0.5 across that set. It's actually close to 20%, right? And the concern is that starts to be an unreasonable risk of type 1 error as opposed to what's going on in each individual one, okay? We can see that our family-wise error rate bound by alpha and our error rate per experiment are C times A, but we're generally going to assume that sort of this is going to be fairly close to that. And this is all based on Bonferroni inequality stuff, which is sort of basis of our Bonferroni test. Right? So the concern that we have with our ANOVA designs, particularly our ANOVA designs that are quite large, right? I have a one-way ANOVA with 6 different groups. makes you should never have a one-way ANOVA comparing 6 different groups, right? You should have more specific hypotheses than, hey, here's 6 different things I can compare. Also, the number of people you would have to adequately power that design. And I have, let's say, 3. If I have 3 groups, how many comparisons can I make? Pairwise comparisons can I make? I have 3 groups. How many comparisons can I make? 3, right? If I have 4 comparisons, how many can I make? More than, what's more than 4? 5. Just guessing. You know what? I like your willingness to just guess. Easy way to do this: C times C minus 1 over 2. Okay? So if I have 3 groups, 3 times 2 divided 6 divided by 2, I can make 3 comparisons. Right? If I've got 4, 6. If I've got 5, 10. Right? If I'm looking possible unique pairwise comparisons that I can go through and make, as my groups start to increase, now this ends up actually being relatively manageable for the most part with one-way ANOVAs, but as soon as we start getting into factorial designs, the number of possible pairwise comparison tests, pairwise tests that we can make starts to explode, right? And so what we need to do is start to think about how do we go through and begin to manage the follow-up tests that we're going to go through and conduct, okay? So general recommendations for follow-up tests with these ANOVA designs. Number 1, be selective, okay? Look at comparisons that are meaningful and that make sense, and if they don't look at them. Don't worry about them. This will get you into trouble with reviewers, because reviewers will want you to look at all possible pairwise comparisons. Tell reviewers, I provided enough descriptive statistics. You can go through and look at it if you want. It's not relevant to my study, right? I'm not going to look at all possible comparisons just because I can, right? If all possible comparisons aren't meaningful and interesting, it's not a good idea to go through and do this because probably what you're going to have to do is correct for all the comparisons that you've made. And I don't want to correct for comparisons that don't have any impact on what I'm trying to demonstrate in the first place, right? And so what we end up doing is we end up imposing a massive correction to run tests that we don't want to look at anyway. And then what happens also if I run 8 different pairwise tests? How many of those are going to come up significant? At least some of them. But if I make a test and it comes up as something that looks like it could be there, and it's not something that's of interest to me, I'm still obligated to go through and talk about it, and then I have to come up with a half-assed explanation for why Group C is different than Group D when I have no theoretical reason to expect those two groups to be different, right? I don't know why they did. That's not the focus of my study. But if I've gone through and I've run all those tests, I'm obligated to talk about it, right? We can't just be like, oh, and so there's this, and the other thing, and then ignore it like it didn't happen, right? So we want to be selective, and we want to choose a strategy that manages our family-wise error, considering both planned and unplanned comparisons, okay? And this is where we start to have to use our heads. SPSS isn't going to do this appropriately for us. SPSS will give us corrections, but SPSS is going to correct for everything. Sometimes we won't want to correct for everything, so we need to be careful on how we're going through and doing this. We have to have, anytime you have an ANOVA design, you should have a written game plan for how you're going to go through and run these follow-up tests. And it should be based on your theory, your hypotheses, and it should hopefully be limited to a few select tests. So again, to drive the idea is to have a good reason for looking at the comparisons that you're wanting to compare. The fact that you're able to do something or have a sufficient reason for actually doing it. Just because I can doesn't mean it's a good idea to go through and do, because what's going to end up happening is I'm going to end up twisting myself up in knots to go through and try and explain why this is different than that, when at the end of the day, I don't care. It doesn't have anything to do with what I actually started to do this for in the first place, okay? in my head, this is what I think, Wilkinson, right? Researchers rarely need to compare all possible means to understand their results or assess their theory. By setting sights on large, they sacrifice power to see small. I like this. Lattice of all possible comparisons, straitjacket, forcing themselves to ward off and restrict research to understand uninteresting hypotheses and reduces them to more meaningful ones. If a specific contrast interests you, examine it. If all interests you, ask yourself why, right? What ends up happening is sometimes you just go through and do stuff without a good reason, thinking about, okay, what happens next? What happens if I do find sort of all things are different than other things, right? Wanting to have good a priori reasons for looking at stuff. Before I run the test, sit down and say, what do I think is going to happen? Based on the literature, based on my understanding and conceptualization, what are the most critical comparisons? What do I expect to happen? What would that mean in terms of theory or practice? These are the things that I'm going to go through and take a look at, okay? Because otherwise, we're just going to run it. And you look at all possible comparisons, weird stuff's going to come up. And what are you then going to do, Chris, when weird stuff comes up?
Pretend it's not weird.
Pretend it's not weird. You make, oh, yeah, of course that one came up. Like all the ones I thought about before didn't, but this one came up. Boy, I'd really like to try and put something in the journal. So here's my explanation for why this thing, comparison that has nothing to do with anything I wrote about in the introduction or even care about, is different, right? It's just bad science. We want to make sure to watch out for that, okay? So, two different types of tests that we can run. We can run a priori tests, we can run post hoc tests. Our a priori tests, these are comparisons that we're going to limit to a small set. They're going to be theoretically meaningful. These are going to be things that we planned before we looked at the results of our omnibus test, okay? Ryan's in the middle of his dissertation right now. Things are looking pretty good, but he's doing a measure validation, so looking at some discriminant convergent relations. I've encouraged him, before you actually go through and look at how your measure relates to these different things, sit down and have a plan. Like, how do you expect, before you looked at them, which one of these correlations do you expect to be the largest relative to what one's the weakest? Have a set plan. So these are the things I'm really interested in looking at before I go through and do it, because we're human beings, and as soon as we look at it, then all of a sudden new ideas start popping into our head about, like, oh, well, for sure, that should be an interesting thing, right? Your a priori comparisons should be chosen before the data are collected, and we're going to look at these as a set of linear contrast independent sample t-tests, okay? And traditionally, what we do is we would go through and conduct these a priori comparisons at per comparison error rates, right? I've called my shot, right? I'm not just firing stuff up from half court, right? I'm saying, this is my shot. I'm going to go through and make it, so I don't need to correct, right? So if I'm just throwing stuff up there, like, okay, I made, 5, but I got to count off 2 because it's slop and luck and stuff like that, right? I'm calling my shot. I'm saying, these are the things that I'm expecting to be different because of these reasons. And if I'm doing that, convention says that I can go through and compare and look at these at per comparison error rates or alpha 0.05. Now, some people will make an argument correcting for family-wise error using a von Fronier Dunn-Siddick, saying, well, I've got 4 comparisons. Even still, just as a conservative, I'm going to go through and make a correction for those different theoretical methodological ideas behind that. But in general, if I've gone through and made my hypotheses before I've conducted the experiment, this is the whole reason I'm doing, to make these comparisons. Again, so the strong methodologists would say, I'm not even going to worry about the omnibus test, or I might run it, I'm just not actually I'm going to ignore it. I'll report it if you want me to report it. What I'm actually going to do is to go through and look at these contrasts. Okay. Post hoc comparisons typically involve the evaluation of all possible pairwise tests. Okay, and with the post hoc comparisons, these are generated after I've taken a look at my observed means, after I've gotten my results, after I've seen where people are at. Then I go through and make decisions about what's interesting and what's not. There's a problem with this, and we'll talk about that in a moment. But what we typically do is take a look at our post hoc procedures, and depending on what procedure we're using, there's a correction for our family-wise error. Really easy to get out of SPSS. The problem is is I've just gone through and corrected for 6, 10 different tests. If 10 different pairwise comparisons aren't interesting or even meaningful, I've still corrected for 10 anyway because I sort of was kind of lazy and didn't think about things on the front end. So, always limited set of planned a priori comparisons are going to be more theoretically and meaningful and defensible than looking at everything that you possibly could, right? If I decided that looking at all possible pairwise comparisons is what I want to do, I need to have a very, very meaningful and compelling rationale for why these data are so exploratory it was impossible for me to even generate some semblance of a hypothesis on the front end, okay? Now, know that this isn't an either or, right? Oftentimes, and probably what's best is, because sometimes there are things we don't anticipate that could be meaningful, right? And so in this situation, it might make sense to have sort of a small set of a priori comparisons. These are the things, this is the heart and soul of my study. These are central to the central comparisons to why I ran the whole thing. But we've gone through the work to collect a bunch of additional, so all this data. There could be other things going on. So these comparisons are post hoc. These ones are a priori. We called our shot on these. These are other things we're just kind of exploratory. We're just kind of seeing what's going on. But then it requires you to sort of know the difference between the two, adjust appropriately for the two, and then also be very explicit up front about this is stuff that was planned, this is stuff that's exploratory, and then taking things forward from there. Questions on the general approach considerations for how we're moving forward with stuff? Okay, cool. So, planned comparisons. One way we can do this, just pairwise tests, okay? If I have an ANOVA with relatively equal cells and relatively equal variances, okay? I've done a pretty good job. I've got a good, tight experimental design. I've done everything sort of appropriately. My numbers of my people are pretty much equal. My variability across, variances across my groups are pretty much equal. What I can do, and if I'm interested in some pairwise comparisons, let's say I've got 3 groups, right? And what I want to do is I want to compare this group and this group and this group and this group. So I want to compare 1 and 2 and 1 and 3, okay? One's my baseline, or one's my control group. I want to compare my 2 and 3 groups to my control group. What I could do with equal cells and equal variances, I could just run a simple pairwise test, okay? And the way I could calculate this, or would calculate this in this situation, I would take the difference between the 2 groups, mean 1 and 2, and then I would divide that by the square root of the mean squared error for group 1 plus the mean squared error for group 2. Okay. What is this formula here? TJ, does this look familiar?
Standard error.
Yeah, it's a standard error. And so what have I functionally conducted here?
You have to see how much variance there is.
What's that?
The variance, yeah.
Well, yeah, so, but just the test statistic. What have I mean, it's basically an independent sample t-test, right? But what's the modification for the t-test that we have run previously up to this point? Nick, do you see it?
There.
Yeah, right, I mean squared error, right? If we think back to our ANOVA test, remember that our mean squared error is basically just the average variability across each one of our cells. The assumption is that the error across group 1, group 2, and group 3, or the variability, the within group variability on group 1, group 2, group 3, is all going to be roughly equal to one another, okay? And so what this test is doing, with our t-test, what goes here?
Standard deviation.
Well, standard deviation, which one? You're on the right track.
Well,
Yeah, my pooled variance, right? What I've done here is I've substituted the pooled variance with the mean squared error from my omnibus ANOVA table, okay? Now, if I've got equal cells and equal variances, that mean squared error is just a nice kind of pooled variance for the whole design, right? So if I'm going through and I've got, remember, group 1, group 2, and group 3. I've got sum of squares 1, sum of squares 2, sum of squares 3, based on my ANOVA design, right? My sum of squares error is just going to be the combination of these 3, right? And if I then take that divided by the degrees of freedom, I get my mean squared error. It's just an aggregate measure of variability within sort of the whole design, right? And this is nice. It's just kind of like a pooled variance estimate. Remember, mean squared is just variance. So on mean squared, this design here, what we've got is we're saying that yes, my mean squared error in my overall ANOVA table provides a good representation of the variability across these groups, right? So I've got equal cells and I've got equal variances. And then what I'm going to do, so I'm going to substitute mean squared error from my ANOVA table for what we would typically think use a pooled variance for just an independent sample t-test. And then my t-critical is going to be my, for a two-tailed test, is going to be t with alpha divided by 2, right? So my two-tailed test with the degrees of freedom error from the overall ANOVA table. Okay. What's advantageous? How does this help us? If we what's going on if we use a degrees of freedom error from our overall ANOVA table? So let's say I've got 20, 20, 20, okay? How many people do I have in my total design? 60, right? Now, if I was just going to compare group 1 and group 2, how many people would I have in that design? 40, right? So if I'm just looking at these two, what's the degrees? If I'm looking at this in an independent sample t-test, what's my degree of freedom? It's going to be 38. But if I use my degrees of freedom from my overall degrees of freedom error from the overall ANOVA table, it's going to be bigger, right? It's going to take the whole sample into account, right? So what we end up with here is a follow-up test, a pairwise test. This is our traditional approach to pairwise contrast in ANOVA. And what this is going to do is it's going to give us a much more powerful test of our simple effects, right? We're using what we would assume with equal variances and equal cells. If each one of the populations from each one of these, that each one of these groups is drawn from, all has equal variance, my variance estimate based on 60 people is going to be much more stable than a variance estimate based on just the 2 groups, right? So I've got a more stable estimate of my error variance, and my degrees of freedom is much larger, right? If I'm looking at a critical value, Chris, is my critical value, what's going to happen to my critical value is my degrees of freedom increase?
It's going to be larger.
My critical value?
Oh no, your critical value.
Critical value is going to go down. Remember, our T distribution approaches a Z distribution as a degrees of freedom increase infinity, right? So I've got a more stable estimate of my error. And my critical values, my benchmark for claiming statistical significance starts to decrease because I'm pulling my degrees of freedom error from my overall ANOVA table as opposed to just using degrees of freedom as we would normally look in a pairwise comparison, a t-test. So we end up getting a more powerful test of our simple effects here. Okay. People kind of seeing what we've got going on with this. Okay. Now, if we have unequal cells and/or unequal variances, so the idea is we lose this advantage, right? This is predicated on the assumption that our mean squared error does a nice job of estimating the variability within each group, right? But if I've got wildly different cell sizes with wildly different variances, this aggregate variance estimate in my mean squared error probably, I don't know if it's a good representation of the variability in group 1 and group 2, right? Maybe group 1 and group 2 have 10 people in it, group 3 has 100, and the variability in group 3 is sort of massively larger than the other 2, right? If I use mean squared error, my mean squared error is way too big, right? If these 2 actually have quite small variances, but the error or variance estimate I'm using is based predominantly on this, and it's way too big, all of a sudden, my test of group 1 and group 2, this starts to become inappropriate. I start to lose confidence that this is, my variance estimate is good and representative of the groups I'm actually comparing. And so in this situation, what we would probably do in the evidence, with evidence of unequal cells or unequal variances, we'd probably just go through and conduct just a independent sample t-test, right? And this is perfectly acceptable using our Boole variance or Welch Saylorwith correction, right? When we run our t-test, unequal variance is assumed, equal variance is not assumed, just default into that, right? So this, and again, remember that ANOVA is when I'm going through and I'm randomizing people to different conditions, having people come in and I've got experimental manipulations in a tight controlled randomized trial, then this starts to work out pretty good. As I start out getting into more applied stuff like clinical, right, when I can't assign people to PTSD or not PTSD groups, right, or substance disorder or not substance disorder groups, all of a sudden my sample sizes get way out of whack, because I've got way more people here than here. I've got looking at different things, and my sort of clinical group often ends up with way more variability in it than my non-clinical group does, or vice versa, right? And so all of a sudden we start to question whether or not this becomes viable and reasonable. And in this case, we can always default just down to running our independent sample t-tests, right? But if we're going to run a tight experimental study, what we can do is capitalize on the full design, and elements of the full design provide us with a more powerful test of the hypothesized effects. Okay. Questions about kind of how we're setting this up? Okay. So again, independent sample t-test. If you just got one or two a priori comparisons, cool, right? You just got a couple pairwise comparisons in this situation. Let's say I've got 3 groups, I want to compare group 1 and 2, group 1 and 3, and my sample sizes are kind of all out of whack, or I have a violation of homogeneity of variance. Just run a couple of independent sample t-tests. That's perfectly fine. Saying because we have violations of the underlying assumptions, we're not sure. I'm not confident that that mean squared error from my overall ANOVA table is a good representation of variability within these individual groups. It's perfectly fine to just drop back and run an independent sample t-test here. Again, in the 2 comparison case, our family-wise error is going to approach 0.15 if both null hypotheses are true, right? Again, if they're not, we don't have to worry about it, right? So again, this can be a reasonable approach. Fairly simple and straightforward. Okay, we're giving up some power, but we're giving up power that we don't know that we deserve because we've made a bunch of violations of our underlying assumptions. All right. Pairwise contrasts are easy. So it's going a little bit different when we get into linear contrast. Anybody ever worked with sort of doing contrasts? Have been exposed to contrast and what contrasts are?
Is that like the orthogonal?
What's up?
Is that like the orthogonal contrast thing?
Yeah, we're not going to worry about orthogonal contrast because no one cares about orthogonal contrast these days. It was a fun thing that people were into, like in the 60s, right? Like that was a cool thing, right? But no one cares about it anymore. So we won't worry about that. But what we see is that if we're talking about linear contrast in general, the nice thing about contrast, or linear contrast, is what we can start to do is look at differences between means or different sets of means. Okay? This ends up providing us with a more flexible approach. If I'm just limiting myself to pairwise contrast, all I can do is compare this group versus that group. When we start to get into linear contrast, what we can do is say, are the levels of my outcome variable in these 2 groups different than these 2 groups? Or is the combination of these 3 different than these 2? Or are these 4 groups different in the overall level than this other group over here that this control? Gives us more variability and flexibility in how we can start to test more interesting and nuanced hypotheses. So we're going through and we're going to combine, start looking at different combination of means. But at the end of the day, in your head, you're always reminding yourself in your head, all we're doing is t-tests. It's just a t-test. At the end of the day, it's just a t-test. It's going to seem really crazy, but it's just a mean-based comparison. Okay? Just a pairwise, or not pairwise, it's just a generalization of our basic t-test here. Okay? So, when we're looking at our linear contrast, what we've done is we've specified some linear combination of means. Okay, so here we have just sort of my linear contrast here is my mean value of group 1 multiplied by some weight, plus a mean value of 2 multiplied by weight, so on and so forth. So just adding sort of weighted mean values. We can write this much easier if we just use our summation, right? This is just saying that my linear contrast is the sum of my weighted means here, okay? This sigma, that just means add everything up, okay? That's just saying that we go through and we add up our series of means here. And so, for example, if my weights, if A is my weight, right, for individual contrast, so if A sub j were equal to 1, my linear contrast is just the sum of my mean values. People see that?
I'm unclear about the weight.
Okay, good, thank you. Then we can call you liars to your face, and everybody's like, oh, we're good with this. The weight is just what you're going through. It's just a number. It's just a weight. We'll see why they're important in a moment, okay? But, Alicia, if I were to take 1 and multiply it by each one of the means in this group, and then add up all of those weighted means weighted as 1, what would I get? If I multiply something by 1, what do I get? Just that something, right? And so each one, if I assign the weight of each one of these to 1, my linear contrast is just the sum of my means.
Where does the weight come
Hold on to that. So just we'll get there, okay? But what happens if I were to set my weight to 1 divided by k, where k is the number of means that I have, right? So I have, let's add 3 means. I've got 5, 8, and 3. Okay. How many means do I have here? 3 means. And so if I apply weights as the inverse of the number of means that I have, so I have 3 means. So if I go L is equal to 1/3 times 5 plus 1/3 times 8 plus 1/3 times 3. What do I get? Christian?
That's 5 1/3.
5 1/3. Okay. What's 16 divided by 3? 5 1/3. Okay. Basically what I've done is I've just taken the average of these means, right? If I run this out, this is just 5 plus 8 plus 3 divided by 3. It's just a different way of expressing sort of the average here, right? So what I've done is I've gone through and assigned a weight of 1/3, so the reciprocal of the number of cells that I have here, multiplying each one of these, it's just giving me the average of those 3 means. Okay.
So like that.
Hold on to that. Okay, I'm less concerned about you knowing that is understanding sort of what the math here. Do you see the math?
Got the math.
Okay, good. All right. So if I'm running a linear contrast, right, this by this fun little psi symbol, right? What we do is when we specify a linear combination so that the sum of my weights is equal to 0, this is what gives us a linear contrast. Okay. So if I've got 3 means, x1, x2, x3, right? And I assign my weights as 1, -1, and 0. If I take 1, add -1, add 0, what do I get? 0. Okay. This is a linear contrast. Okay. So if I go through and run my contrast, so I weight this is 1, this is -1, and this is 0. Tomorrow, what have I created here in my contrast? What am I comparing in my contrast?
1 and 2.
I'm functionally comparing group 1 and group group 2 is if I go through and run that out, 1 times x1 plus 1 times 1 plus -1 times x1, so that's -x2 plus 0, that falls out. What I've assigned with my linear contrast here is a comparison between groups 1 and 2. Group 3 falls away, and I've just got a comparison between these two groups. Okay. What if I go through and I assign A1, my first weight to be 1/2, second weight to be 1/2, my third weight to be -1. Again, 1/2 plus 1/2 is 1, plus -1 is 0. I've got a linear contrast. Right? If I go through and assign those weights, Nick, what have I essentially done here?
Comparing x1, x2 to x3.
No. I've got the combination of x1 and x2 compared against 3, right? So I'm saying, what's the difference between group 3 against the average of group 1 and 2, okay? And this is where things start to become helpful, is because what I can do with these linear contrasts is it gives me a great deal of flexibility in terms of how I want to compare my groups. With just pairwise contrast, I can say this group versus that group, right? Well, what if, let's say I have, let's say I've got an active treatment group, and I've got 2 controls. I've got a weightless control, and then just a non-specific therapy control. I might be interested in, does my active treatment group outperform sort of the combination of my 2 control groups, right? So what I could do in this, if, we'll probably switch around the signs, but what I could do is I can compare, with linear contrast, I can compare my group against the combination of these other 2 groups, right? And that's actually kind of a compelling thing. Not only does my group do individually better than these 2 groups, it does better than the combination of these 2 groups put together, okay? Or if I've got 2 active groups and 2 control groups, I can compare the average of the 2 active groups against the average of the 2 control groups and sort of see if there's a difference there, right? So what, why do I assign weights? Assigning weights allows me to go through and start to bundle mathematically different groups together and arrange them in different types of comparisons, okay? So these weights are completely up to me, right? The only thing that's restricting sort of what the numbers I assign to that weights, they just have to be proportional so that they end up sort of resulting in the comparison that I want to make. Okay. Questions about this? People seeing what's going on here? Okay, so how do we go through and select these coefficients? First thing we want to do, we want to identify the set of groups or treatments to be compared. For this contrast, which groups do I want to differentiate or compare? Then what I'm going to do is I'm going to assign weights as the reciprocal of the number of treatments in that set. Reciprocal just means flip it over, 1 over, right? And then what I'm going to do is I'm going to assign coefficients of one of those groups to be negative. Generally what I'm going to do is whatever group that I think is going to be lower than the other group, I'm going to give that group the negative weights, okay? So let's say I've got 5 minutes, x1 to x5. What I want to do is I want to take a look at the combination of x1 and x2 against the combination of these 3 groups, okay? So I see, identify the treatments to be compared. I want to go these 2 against these 3. So we've got that taken care of. Then what I'm going to do is I'm going to assign weights as the reciprocal of the number of treatments in each set. So how many groups do I have here?
2.
So what's my weight going to be for those groups? 1/2. This, what's my weight's going to be? 1/3. Exactly, right? And then what I'm going to do is I'm going to assign groups to be negative in one of those, right? Now, in this comparison to the way I've weighted this, what group am I expecting to outperform the other group on whatever it is that we're looking at? Yeah, group 1. Yeah, I'm expecting this group to score higher than that group, right? If I was flipped around, I could just make these negative and these positive, right? But if I go through, I take 1/2 plus 1/2, minus 1/3 minus 1/3 minus 1/3, my weights sum to 0. I've got a linear contrast here, okay? And so then what we can see, we can write the sum of my weighted means is going to be equal to 1/2 times x1 plus x2 minus 1/3 plus x3, x4, x5. that gives me my, my linear contrast here, okay? You'll see how we set that up. All right, if we go through and we set our linear coefficients so that the absolute value of the sum is equal to 2, then we have not only a linear contrast, but my linear contrast equals a standard set. And this starts to become important when we're calculating effect sizes. As long as my weights here sum to 0, it's fine. They can be whatever they want to be. But when I go through and I add them all up and the absolute value sum to 2, that means I've got a standard set. So if I take 1/2 plus 1/2 is equal to 1, plus 1/3 plus 1/3 plus 1/3 is equal to 1, add those up, that's 2, I've got a standard set, right? But I could just as easily set this equal to, I could set this to 3, and that to 3, and this to 2, 2, and 2, or -2, -2, -2. And so I've got 3, 3, -2, -2, -2. Do I have a linear contrast here? Yep. 3 plus 3 is 6, minus 2 minus 2 minus 2 is -6, sums to 0. It's going to be, I'm going to get the exact same answer as I did before. Problem is it's an issue of scaling, right? What is then going to happen, so the difference between those two, is it going to be on the same scale as the actual thing, and that kind of throws some stuff off, but there are reasons why we might want to play with this. So your weights can be an infinite number of values, right? You just need to make sure that they sum to 0, and generally it's just easier for using a standard set for later calculations that we'll make. Okay. Questions about this? All right. Now, when we're doing this by hand, if we have dramatically different sample sizes, this starts to complicate the calculation of these contrasts. Things start to get tricky, and other things start to break down. So again, thinking about this whole process as being developed within the context of nice, tight experimental designs, as opposed to stuff that turns into a free-for-all. But in theory, this is how we're sort of going through and calculating things. Okay. All right. So, classic tests within the context of our contrast. What we can do is we can calculate a sum of squares based on the treatment means and our associated weight. So this is the value of my contrast, okay? Psi here is just the value of my contrast. It's going to be the sum of my weighted means, right? So just right there. Based on this, I calculate my sum of squares contrast as equal to n, the number of people I assume I've got, because this assumes I have equal cell sizes across each one of these. Cell size times the square of whatever my contrast value is here, over the sum of my squared weights is going to be equal to n times sort of the value of my contrast here over the sum of my squared weights. This gives me my sum of squares contrast. Okay. If we have a design with unequal samples, then we have to make an adjustment on my sum of squares contrast. This is now going to be my squared contrast value over the sum of my squared weights over sort of the individual n's for that cell. So let's go through and say I've got 3 means. 10 values observations within each cell. Means 1.5, 2, and 3. So we're going to say I want to go through and I'm going to set my first weight to 1/2, second weight to 1/2, and my third weight to -1/3. Okay. Chris, who am I? Sort of what comparison am I making here?
Making the comparison with you're looking at groups 1 and 2 similarly, and you're comparing it to group 3. Yeah.
So I've got 1 and 2 versus 3 here.
Yeah.
Okay. That's so this contrast is what I'm sort of wanting to do. This is of interest to me, right? So what I can do then is I can say the value of my contrast is going to be 1/2 times 1/5 plus 1/2 times 2 minus 1 times 3. Value of my contrast is -1.25. Someone tell me conceptually what the value of my contrast represents. You got it, Chris?
The degrees of which your third group is larger than your first two groups.
Yep. This is just the difference in the average of groups 1 and 2 versus 3.
You switch like the signs every single slide, and I'm always like, and the first one was like right, and then the next one I was like,
No, yeah,
this one
but you got it, right? So we've got 3 is a larger value, right? And so the combination of 1 and 2, right? If I take 2, the average of 1.5 and 2 is going to be 1.75. Subtract, you get 1.25, right? So this is just a difference in means, right? And so this is why, so literally in units, group 3 is 1.25 units higher than the combination of groups 1 and 2. This is just, now if we have unequal means, then we start to get weighted means, and then so then it starts to get a little bit more complicated. But when we have identical, it's just sort of the difference in the average means, essentially. Okay. So what we can then do, because we've got the value of our contrast, we can go through and calculate the sum squares of our contrast at 10, so that's the number of 10 good people in each cell, times the value of my contrast squared, over the sum of my squared weights, right? So I've got 1/2 squared plus 1/2 squared plus -1 squared. So we square those, add those up. This gives me my sum of squares contrast. And so then what I do, because my linear contrast gives me a 1 degree of freedom test, right? My sum of squares contrast is equal to my mean squared contrast, because my degrees of freedom is only 1, right? We go from sum of squares to mean squared by taking the sum squares divided by degrees of freedom. If I take sum squares contrast divided by 1, I get the same value, right? It's giving me my mean squared. And what I can do is I can take that mean squared contrast and divide it by the error term from my overall ANOVA table, which gives me an F test, right? So what I would do is I would take my mean squared for my contrast, 10.42, would divide it by the mean squared error, whatever that is from my ANOVA table. This is going to give me an F statistic that I can evaluate against an F with 1, and what are the degrees of freedom areas within the contact pulled from my ANOVA table. Okay. Questions about this procedure? Okay, so basically, as long as you're square on the math, as long as you go through and you've got your weights assigned correctly, it's actually not that terrible or difficult to go through and actually calculate, right? Because the value of my contrast is just the average difference in my means. My sum squares contrast is just a statistic that's calculated based on my weights, right? And the value of my contrast. And I can just go through and pull error terms. And this is why I walked you guys through so what things are in that ANOVA table and where they're coming from. This is just our mean squared error that we use and sort of use as the error term for our overall ANOVA setup, and just using that to go through the test. So the difference in the average between groups 1 and 2 with 3. So this is how the classic approach to, if you look at old textbooks from like the 50s and 60s, this is the appropriate way to go through and do things, right? This is not how SPSS goes through and does things, right? SPSS formula, when it's calculating linear contrast in SPSS won't be given as an F statistic. They'll be given as a T, okay? And basically what's going on, the T statistic here in SPSS is just, once again, the value of your contrast divided by the standard error of your contrast. Standard error of your contrast in SPSS is calculated as the mean squared error. Again, this is pulled out of your ANOVA table, times the sum of your squared weights over your individual sample sizes, right? So this would be 1/2 squared over 10 plus 1/2 squared over 10 plus -1 over 10 squared. add those up, right? And again, calculated, compared against a critical value of T with degrees of freedom set as whatever degrees of freedom are for the mean squared error. If I have a balanced design, right? If I have the same number of people in all of my cells, this statistic and the F statistic that I get is exactly the same. As sort of things start to change up, then we get some variability here. As we go through, and I have you hand calculate things, use this formula, okay? Don't worry about F's because then we have problems with sort of different stuff. Just use this formula. This is a fine formula for going through. I wanted to show you guys sort of this classic approach for anybody who's ever been through an ANOVA course before and is used to seeing F's as the test for contrasts. And it's likely that you'll run into this down the road. And so if you see F's for a pairwise comparison, sort of this is kind of what's going on here. So SPSS also provides corrected tests and standard errors for violations of a homogeneity of variance. This is the formula that SPSS uses. I had to go through and how I spend my free time and my Saturday nights with a tumbler of whiskey looking through algorithms for sort of how people are actually getting numbers that they're actually trying to get. This is, so basically we've got an adjustment for your standard error and for an adjustment on your degrees of freedom. And these are the tests. Now the interesting is SPSS does this. When you go through and you ask for your contrast, it'll say equal variance is assumed, equal variance is not assumed, right? Which is nice because you're like, oh, if I have a violation of homogeneity of variance, then this gives me a corrected test and I'm good to go. Probably. I haven't found other programs that do this. And if you guys didn't think I was cool enough, I found a reference for this and then actually bought the textbook from like the 70s that actually sort of was cited in this. I don't know what the evidence is for this procedure or how well it does what it's supposed to do. We can take on faith that SPSS has just implemented something that's a good way to do things. I question the fact because no other statistical program actually provides this. I assume if it was a good thing or so not without controversy, other programs would provide it. I haven't found that yet. But it's probably fine. You just wanting to know, again, this starts to get in maybe more depth than anybody's interested in, but wanting to know that sort of what I'm reporting actually has sort of a strong scientific basis. I have a textbook from the 60s that says maybe this, right, and SPSS does it. Just wanting to sort of be worried about this. For sort of SATA will not give you this because SATA doesn't recognize this as a thing. It takes a different approach. We can talk about how that goes through and does it, so it actually has something with a little bit more sort of at least documented history of sort of how to adjust for things. So I'm not saying don't do this or use this, and if you have violations of homogeneity of variance, this is probably what you should be reporting. I'm just saying that I can't independently verify that yes, this is consistent with best practice methodologies for this issue. Okay. Questions on this?
So like put Crystal Pepsi up there. Like it's okay, but you should probably just drink regular Pepsi so you don't really know what Crystal Pepsi is.
What's
I've
that?
never seen Crystal Pepsi.
Anybody know what Crystal Pepsi is?
Yeah, it looks like that. It's just Pepsi that's like clear.
Yeah, Coke did it too.
What's up?
Coke did it too.
Yeah. Yeah, it was like early 90s? Early 90s?
Does it taste the same?
Yeah, it was supposed to say, they brought it back
Supposed to.
like 2 years ago.
Is Crystal Pepsi around?
They brought it back 2 years ago for like a small amount of time. I think no one went.
bought it.
Like, I don't know. It was at my local grocery store.
Yeah. The idea is like at the time they were marketing as, because you got like 7-Up and Sprite was on the rise, right? Oh, we got this clear you got this clear soda that's probably more healthy because it's not brown like ditch water, right? So here's Crystal Pepsi. It's just weird, right? It was not a home run for Pepsi or Coke. So again, yeah, I can't verify just whether that is it's something that is. It's just, can't sort of independently verify the quality of it. Okay. Okay. So managing our family-wise error here. Okay. We generally, again, convention says that we would test our planned contrasts at per comparison error rates. Okay. If I've called my shot on the front end, I don't need to worry about implementing additional corrections for multiple tests. But some people will continue to say, well, you know, we should probably, in terms of being conservative, we probably should continue to implement some corrections. Again, if I call my shot 4 times and each one of those times are wrong, I still have about a 20% chance of identifying one of those contrasts as meeting conventional benchmarks for statistical significance, even though in actual fact the analysis is true. Okay, and so a couple of things we can do, right? One, we can reduce the number of contrasts. If you have 15 a priori contrasts, no, you don't. Like, you shouldn't have that many a priori contrasts, right? You should try to reduce that down and say what's the most meaningful here. So we can reduce the number of contrasts we're running, or we can select a more stringent alpha level to start to manage that family-wise comparison. Okay, and the 2 things that we should be using for planned comparisons: Bonferroni test. Okay, Bonferroni test, we're correcting for family-wise error. Pretty straightforward. We're just taking our alpha level and divided by the number of comparisons. Show of hands if you're familiar with Bonferroni. Just 2. Okay, cool. People love Bonferroni. People
love it.
People will go nuts over Bonferroni. Like 2% of the population is using Bonferroni corrections correctly. Okay, this should be very sort of a slight adjustment for a very small set of comparisons. Right. The idea is that the probability of one or more events can never exceed the sum of their individual probabilities. So what we do is we take the number, if I want my alpha level to be 0.05, and I divide that by the number of comparisons that I'm making. So the likelihood of me making at least one type 1 error across the set of these is never going to exceed the original 0.05, right? So again, if I say my alpha is 0.05, what I would do here, so with alpha 0.05, someone else with a calculator. Tomorrow, what's 0.05 divided by 3? Chris C. carrying water for everybody here.
0167.
What is it?
0.0167.
0.0167. Okay. So what I would do with the Bonferroni, okay, everybody look me in the eyes right now. Nicholas, or Christopher, look me in the eyes right now. Bonferroni is a correction on your alpha level. It's not a correction on your t-statistic. It's not a correction on your critical value. It is a correction on your p-value. Do not create a whole new t-statistic or a whole new critical value for Bonferroni. Don't do it, okay? What we're doing with Bonferroni is we go through, let's say I have 3 comparisons, right? And I'm going to Bonferroni correct for that. I'm going to take 0.05, divided by 3. And so my new criteria for claiming statistical significance is 0.0167. So if I go through and I run my statistical test, if I run my comparison, and I get a p-value that's less than 0.0167, I get to claim statistical significance. If it's above 0.0167, then I failed to establish statistical significance. This is all we're doing here is we're just changing that p-value threshold from 0.05 to whatever it is with my Bonferroni correction. Okay, so make that so with this. This is not, so don't use adjusted. So what ends up happening? People start looking at the test statistic for a critical value for p equal 0.0167, and then they create a new test, and then it's screwing up confidence intervals, you're overthinking it, right? All you need to do is setting your new alpha level, not 0.05, it's now 0.0167, and then you just compare your p-values to that. Okay? Now, thing is, bond for only correction appropriate for a small number of planned contrasts, okay? You should never apply bond for only to all possible pairwise comparisons. Now, if you have 3 groups, right, and you only have 3 comparisons, it's probably not so bad. This is not a post hoc test. Even though it's advertised as one in SPSS and a number of different statistical packages, this was not developed as a post hoc test. Because what's going to happen is it's going to create an unreasonable correction for you to achieve statistical significance, and then all of a sudden your type 2 error is exploding through the roof, okay? You will run into this where you'll have reviewers telling you you need to bond for and correct for everything that you looked at. That's categorically false. It's an irresponsible use of this procedure, okay? So don't do it unless you want your alpha level to be 0.00005, right? So just know sort of when to go through and use this, okay? Other option is density correction. It's a little bit more precise than bond firming. Here we're taking our new alpha level is 1 minus our alpha time, or to the power of 1 over the number of corrections. A little bit more precise control of family-wise error, but the difference between density and alpha, they're going to end up being fairly similar. Okay, so for 3, if I take 1 minus alpha and 1 over 3, there we go, 0.95, take that to the 2/3, 1. Oh, of course. Not 2/3. So I get 0.017, it's 0.0695, right? So they're pretty close. Duncidec is a little bit more lenient than Bonferroni, but so 2 different options. But neither one of these are post hoc corrections. Both of these are to be used to manage family-wise error for a small set of comparisons. Okay. Questions on this? All right. Confidence intervals and effect size on our contrasts. This is pretty straightforward, actually. There's not anything too crazy in terms of confidence intervals. Our confidence interval is just going to be for our pairwise test. It's going to be the difference between our 2 groups, plus or minus our critical value here, multiplied by our standard error. Here you want to make sure that the standard error you're using is the same as you use for our hypotheses test. This is why we're going with crystal PSYC, because the classic F value doesn't have like a proper standard error measure there, right? Using the T formula just makes it easier to calculate a confidence interval around your pairwise tests here, okay? Same thing for your 95% confidence interval around your linear contrast. Same thing, just the value of your contrast plus or minus critical value times your standard error. Okay. So nothing new or interesting here. This is just the same confidence intervals that you've been calculating since the beginning of this semester. Effect size, a couple different options here. For my pairwise contrast, probably what we're going to take, we could go through and take the difference between my 2 contrasts, or my 2 groups, and divide it by a pooled standard deviation for those two groups, right? So this is just basically a version of Hedges G. I mean, it's not an independent sample t-test, but it's basically sort of we're doing the same thing. Other option that we can use here, if we take sort of 4-hour linear contrast, we take the value of our contrast, and this is why it's important to achieve that standard set, right, where all the sum of the absolute value of your weights equals 2. That means the value of your contrast is going to be in the same units as error, right? And then what we need to do is divide that by some standard deviation of error. This is where we get into some differences in terms of options that we can use. We can, as our error term, we can just take the square root of our mean squared error from our overall ANOVA table and just use that, okay? Why? So someone tell me why this works. Someone tell me about what my mean squared error is?
Between group differences.
Not between, my within group differences, right? And so if I have equal cell sizes and I have no violations of homogeneity of variance, right? Basically the variability in each one of my populations is expected to be about equal. My sample sizes are all pretty much equal. Then my mean squared error is just a nice aggregate. It's kind of like a giant pooled variance for the whole design, right? And if I have no concerns that the variance is different across my different groups, mean squared error is a nice, easy, just kind of a thing about mean squared error, it's just like a big pooled variance, right? And so what we can do, if we've done a really nice design where we got balanced and we got no violations of homogeneity of variance for my contrasts, it's reasonable to just go through and pull the square root of my mean squared error, right? Because that's just an error variance. You can go through and do that, okay? If, however, I'm worried about homogeneity of variance, right? What I can do, but I've got equal cell sizes, right? I've got so the same number of people in each one. But I got a violation. My Levine's test came up hot, right? And so I'm like, I've got maybe violation of homogeneity of variance there. What I might do is I could take the square root of the average variances across the samples in question, right? So what I could do is say, I'm going to take variance for 1 plus variance for 2 plus variance for 4, okay? So I'm comparing groups 2 and 4 against group 1, okay? If I got the same number of people in each group, I just take the average, or oops, not 2, 3. Take the average of those variances and just go through and square that and just take a look at the ones that I'm sort of interested in instead of pulling from the mean squared error from the full design. Okay, and so this might be an option if I have some concerns about homogeneity of variance across all the cells, across all the different groups in my analyses. What I could also do if I have not only unequal sample sizes and violations of homogeneity of variance, what I can do is modify my pooled formula and just calculate a pooled variance estimate here, okay? So not only do I have unequal sample sizes, or unequal variances, now I also have unequal sample sizes, right? So I can't just take an average value because that assumes that I've got the same number of people in each, right? But what I can do is I can modify my pooled variance, right? Is going to be N1 minus 1 times my first variance plus N2 minus 1 times my second variance plus N4 minus 1 times my fourth variance. Take that over N1 plus N2 plus N4 minus 3, right? And I can do this for however many I want, right? It's just expanding out that weighted variance estimate, right? And so if I'm concerned that I have unequal sample size and I violate homogeneity of variance, this might be a better option than one of these other ones, right? Or if I have a nice control group and so that's what I want to do, I want to sort of structure my effect size within standard deviation units of sort of this control where everybody's just kind of coming in a baseline. I can substitute standard deviation of control group in there. So, but again, if we're gonna just plug the value of my contrast in for my effect size here, have to make sure that my coefficients form a standard set, okay? Both of these, for my t-test, both of these weights will give me the exact same value, okay? The problem is that this forms a standard set, this doesn't, okay? Both are linear contrasts. In the statistical test, both of those are gonna work, except it's just that the value of my contrast here is gonna be something I can plug straight in up here to my effect size. This one is gonna be a little bit more tricky. All right, questions on any of this? All right. Okay, we're not gonna lose. Quick, just to touch base on post hocs here. So what we've been talking about up to this point is working with the set plan comparison. These are things that I've called my shot on the front end, right? But there are going to be situations where maybe this isn't sort of, I might be having an area that's so new that really I don't have good, strong ideas about sort of what might happen within the context of this study. Typically, when we're evaluating all possible pairwise convert, we're just kind of throwing broad, we're shotgunning stuff. We're going to hit some stuff we want, we're going to hit some stuff that we don't want, and it starts to make it very difficult. In this net set, you'll have to go through and interpret the post hoc analyses, and there's going to be a whole lot of things you have to go through and account for. It's a giant pain in the ass because there's so many different things you have to go through and say, well, there's this, and maybe this is going on, but these ones aren't. It's just a lot to go through and deal with, right? And the concern is if we go through and we do look at all possible pairwise comparisons, we start to lose considerable power because, again, what we're doing is we're correcting for comparisons that we don't really care about, right? But if we have a lot of different hypotheses, purely exploratory analyses, post hoc comparisons can be something that's useful to go through and implement. With our post hoc procedures, we've got a number of different possibilities. Fisher's is a classic, Tukey, everybody loves Tukey, and a couple variations on that. Some other more, this is also something that happened in the 60s, right? People are super down into developing post hoc tests, right? So we've got a lot of different options here. The ones people use are actually probably a much smaller subset of those, but we'll go through next Wednesday and talk about sort of what some of these sort of differences are. So next Wednesday, we'll start with running through in a different set. We'll start and run through, just give examples of linear contrasts, so you kind of see what those are and how to go through and calculate those, interpret those, and then we'll finish up with post hoc comparisons on Wednesday, and that will probably actually take most of the class. Okay. This will be the first time that we're behind schedule all semester, which I'm pretty excited about. So, cool. All right. Thanks. You guys are champions. Let me know if you run into questions on this set. Hopefully people are in the mix of it. So again, just make sure in your write-up you've got things structured. Make sure for this one, I don't think sort of a lot of things that trip people up on the last one I have to worry about. Just make sure that you're reading through it carefully and answering all components of the question, right? If you've done something, like writing something, gets you like half the points, right? So a bit like if you do something, right, it will go through. And so just make sure that you've gone through and make sure that you double check to make sure that you've answered all elements of the question